Hello students, welcome back. In this video, we'll be discussing all the questions that appeared in the midterm examination of the last year. Say question number 1, it contained 5 parts. We will answer all these questions one by one. So the question number 1A is, what is an LTI system? The answer is LTI stands for linear and time invariant systems. So these are a class of systems used in signals and systems that are both linear as well as time invariant. Now, as we know that linear systems are those which follows the properties of additivity and homogeneity. So in other words, for a system T over the time T composed of signal x1t and x2t with outputs y1t in response to the signal x1t and y2t in response to the signal x2t can be written as combinedly for a linear system is a transformation of, so this says a1 x1t this multiplication, it is the homogeneity, and this plus is the additive properties. So this combines both the properties, homogeneity and the additivity. So the transformation of the signal a1 x1t plus a2 x2t can be written as equal to a1 and the transformation on the signal x1t plus a2 transformation of x2t, which can be written as a1 y1t, a2 y1t, y2t. So time invariant. Now the second is a time invariance, are systems where the output for a particular input does not change depending on when that input was applied. That is, if xt produces yt, then x of n plus t will produce y of n plus t. So this is how you need to write the answer for time invariant, linear and time invariant systems. The part B of the question was, relate Z transform with the Laplace transform. So the Laplace transform, as we know, it converts the integral differential equation into the algebraic equation. In a similar manner, the Z transform converts the difference equation into the algebraic equation. The Laplace transform is used to analyze continuous time system, whereas the discrete time counterparts are analyzed using the Z transform. We know from our discussion in the class that x of z for the discrete time system can be written as summation of n from 0 to infinity of x of nt z power of minus n. So if we define z is equal to e power of st, so the z transform becomes proportional to the Laplace transform. So this must be very clearly noticed. So if we define z is equal to e power of st, then the z transform will become the Laplace transform. So instead of writing xz, you can then write x of e power of st, summation of 0 to infinity of x nt e power of s nt. Now, as the sampling interval t goes to 0, so we will have limit t tending to 0. So if you have the sampling interval as very less, tending to 0, so then this term x e power of st for t is equal to limit t tending to 0 of this particular, say, that is n from 0 to infinity summation of x tn e power of stn t. So which can be then written as equal to the, when you sum all these discrete values, that is nothing but the integrals. So it is nothing but the integration from 0 to infinity of xt e power of a minus st dt, which is nothing but the axis itself. Or in summary, we can conclude that the Z transform times the sampling interval t of a discrete time signal x of n(t) approaches as t approaches to 0, the Laplace transform of the underlying continuous time system. Then the difference, third question was, C part was difference between the linear and non-linear systems. We know what a system, what the linear system is. A linear system is one that satisfies two properties, and these are the additive properties and the homogeneity properties. So these two additives can be written together for two signals x1t and x2t. Now supposing if the excitation x1t produces the response y1t and the excitation x2t produces y2t, then the homogeneity, that is A times of x1t and B times of x2t, will produce the signal yt, will produce the signal yt, which is a transformation of the combined homogeneity and additive property of the x1t and the x2t, which can be written as A times of y1t and B times of y2t. So example of a linear time system or linear system is yt is equal to x multiplied by sine of t. So this is an example of a linear. So x in this case is the homogeneity and with the sine signal. A system that does not satisfy the linearity will be called as a nonlinear system. For example, if you have an equation yt is equal to a xt plus b, so this will be a system which is a nonlinear system. Part D of the question was differentiate between the time variance and the time invariance. We know even from our previous discussion that a time invariance system, we discussed it here. Time invariant are the systems where the output for a particular input does not change depending upon when that input was applied. That is, if xt produces yt, then x of nt will n plus t will produce y of n plus t. So similarly, so the difference is the time invariance system are those in which the response of a system to an excitation or the input is not a function of time. Whereas time variance is those systems where they, if the response to an input alters with the time, then it is a time variance. Time invariant system, a shifted input will produce the same amount of shift in the output response. But in the time variance, a time varying system will produce a response which does not match with the shifted version of the original unshifted response, shifted by the same amount. Part E of the question is write the properties of the impulse function. We know what the impulse function is. The impulse function is one which gives us the output, which is just an impulse, a sharp rising pulse at a time t is equal to 0. So the different properties of the unit impulse function are 0 dot del of t will be equal to 0, del t is equal to minus of t, will be equal to del of minus t, del of t minus a is equal to del of a minus t, del t dot ft is equal to f0 dot del t. Del t dot t minus a can be written as a of t minus a. Then if you have del of at, it can be written as 1 over a times t, where a is not equal to 0. And the last one is the integral from minus infinity to t of del t d tau is equal to ut. Similarly, if you differentiate ut, you will arrive at the impulse pulse. But if you integrate all those impulses, then that will be equal to the ut. Question number 2. What do you mean by jet transform? Find the jet transform of xn is equal to cos n omega dot un. We know what the jet transform is. The jet transform converts a discrete time signal into a complex frequency domain, that is z or the z domain or the z plane representation. It can be considered as a discrete time equivalent of the Laplace transform. Mathematically, we can write z of xn is equal to x of z. So this is how we write the jet transform, is equal to the summation of 0 to infinity of xn z power of minus n. This is how we represent the jet transform in the discrete time signals. Now, to find out the jet transform of the given signal, that is this signal, so we can use the Euler's identity for the cos of n omega t. We know what cos of n omega t is equal to, is half e power of j omega n plus e power of minus j omega n. So therefore, the jet transform can be written as the summation of cos of n omega, which is nothing but half of e power of j omega n plus e power of minus j omega n dot z power of minus n, z power of minus n. Now you can expand this and write it this along with this one and separate them. Similarly, then further to this, we can write this as equal to half of this part will be equal to the summation of, this is a series. So this will become as 1 over e power of j omega z power of minus 1. And this series, summation of this series will become as 1 over 1 minus e power of j minus j omega z power of minus 1, which can further be written as z over this z power of minus 1 taking as a LCM. So this will go at the top. So this will be z over z minus e power of j omega, plus this part will become as z over z minus e power of minus j omega. Taking the LCM, you will arrive at this. And finally, when solving this, so you can go back and use the Euler's form. So therefore, x of z will be equal to z minus cos omega over z square minus 2z cos omega plus 1. Now the next thing is to find out the ROC for this part. So the ROC, this series will converge if z is greater than 1. Mod of z is greater than 1. Therefore, the ROC of the z transform of cos of omega is for mod z greater than 1. So this completes the answer for find the z transform of the signal cos of n omega. Second question was that a waveform was given and you were asked to synthesize this particular waveform. Now the solution for this will be how to synthesize is, if you look at this particular waveform, you find that this waveform composed of many waveforms. For example, before we go to the solution, as you can see, this particular signal, a rising ramp, so it is supposed to continue infinitely, but it is stopped when the function t is equal to its value at 0, the value is 2. It is stopped here. So how to stop is, you need to cancel this effect. So you need to add another pulse which will cancel this rising effect. So this can be seen here in the first part of the question. As you see, the equation will tend to go to the infinity, but it is stopped at 2 when t is equal to 1 by adding a negative pulse to this given pulse. Then you need to add another pulse which is a negative unit step. So you can see this, a unit step is added to it. So at t is equal to 1, a negative pulse is added to it. So the negative pulse is added to it. But again, you know that this pulse will continue to t is equal to infinity, but you need to stop it at t is equal to 2. So you need to cancel this effect and add a positive pulse to it. So you can see at t is equal to 2, we add a unit step positive at t is equal to 2, shifted. So I add u of t minus 2. But again, you see, if you apply a positive unit step, this will continue to infinite. You need to stop this pulse and make it as a falling ramp. So this falling ramp, as you can see here, you need to give a falling ramp here at 2, as you can see, and again at point 3, t is equal to 3, you need to stop it going further. So I add a positive ramp to this. So in all, how many pulses? You see f of 1t and f of 2t to cancel this effect, f of 3t, this a negative going unit step function, and to cancel this effect, f of 4t, a positive going unit step function, and a falling ramp. So for this, you need to add a negative ramp and a positive ramp to cancel the effect. So in all, total 6 functions. So these 6 functions can be written as this way: f of t is equal to summation of all these 6 functions. So now you write down the values of these functions. F of 1t, this is f of 1t, which is 2 times of rt. I can write it this way. So f of t is a negative rising negative or a falling ramp, which is of minus 2 times of rt minus a shifted. So I write this value f2t. My f3 is a unit step function of shifted by 1 unit. So minus of ut minus 1. Then a shifted positive going ut minus 2, this one. Then a negative going ramp of the value 2 times of rt minus shifted by 2 units, and shifted by 3 units, a positive going ramp. So this way. So in terms of ut, I can add the rt is equal to t into ut. I know what the ramp is represented by a time varying. So it is a time varying. So RT is a time varying t times of ut. So this will become a t 2 times of t ut. So this will become 2 times of shifted t minus 1 ut minus 1. This will become shifted by 2 units. So is a unit step function. This is a unit ramp function by shifted by 2 units. So this will be 2 times of t minus 2 ut minus 2. And this one is a time shifted ramp when t is equal to 3. So this will be 2 times of t minus 3 ut minus 3. Question number 3. What do you mean by the Laplace transform? And find the Laplace transform of ft sine of omega t for t going from the limit 0 to t by 2. The solution to this will be a little tricky. So to understand the question very carefully, let's first reply what is the Laplace transform. So the Laplace transform was given in question number 1 at the here. Question number. So if you go back here, a Laplace transform is one that is used to convert a integral differential equation into an algebraic equation. So the Laplace transform is used for the time varying signals to convert the integral differential equation into the algebraic equation. Now, with that definition, now let's come to the solution to the question ft. Find the Laplace transform of ft sine of omega t for t change varying from 0 to t by 2. Let's see. Is a sine function. We know the sine function is represented as this way. So it is 0 and the time t is here. T by 2 will be here. So you need to give the solution to sine omega t for the range t from 0 to t by 2. You don't need to consider the full wave, but only the wave from here to here, 0 to t by 2. So how will you get this t by 2? If you cancel the complete other way, after this you need to cancel this one. So you need to add a reverse pulse to this one so that this effect is cancelled and you get only this wave. So to the pure sine omega t, if you add a shifted sine omega t by t by 2, then you get the pulse which is just only the pulse 0 to t by 2. So this 0 to t by 2, we'll see to it. Let's say given signal. So this signal V1t is the signal given in the question sine of omega. This is a pure sine signal. This is a pure sine signal which can be written as V1 is equal to sine omega t into ut. V2t is a shifted of this pure sine wave and it is shifted by t by 2. So therefore I can write sine omega t can be written as t minus t by 2 and ut minus t by 2. But you were asked to find out the response to only between 0 to t by 2. So you need to add these two functions together so that you get only the pulse that is 0 to. So you can just see to it how exactly you get it. So what exactly we mean by saying so is let me use the pencil and say that to this one, let's say you have this pure sine wave and continuing this way. So this is 0, this is t by 2 and this is t. You are asked to find out the response only from 0 to t by 2. So you are asked to find out only this response. Only this response. So how do you get this pulse? This pulse is obtained by, so you just have a look. Given this pure sine wave and you add to this a shifted, you need to shift it by this much. So you can see if you add them, this will get cancelled with this one, this will get cancelled with this one, this will get cancelled with this and so on. So if you add these two signals, let's say this is y1t and this is y2t. If you add them, you will get yt is a signal which is just a signal from 0 to t by 2. And you are asked to find out the Laplace of this one. Okay, fine. Now you understand those and come back to it. So you need to add these two signals. Adding these two, we get Vt is equal to sine of omega t plus this shifted sine of omega t minus t by 2 ut minus t by 2. And which will be equal to omega over s square plus omega square plus e power of t by 2 s into fs. So you know the Laplace of sine of omega t is equal to omega upon s square plus omega square, and the Laplace of a shifted function is e power of minus a. So this a is t by 2. E power of minus a by t by 2 s, and the function fs. The fs is this function. So therefore, we can write for this fs as equal to omega by s square plus omega square. That is, this will become as this. So taking omega or s square plus omega square as common, so we will get as omega by s square plus omega square bracket 1 plus e power of minus a s. A is t by 2 s. Let's consider another question. Consider a RC circuit as shown in the figure. The switch is closed at time t is equal to 0. Find the current through and the voltage across the resistor and the capacitors. So we can apply the KVL. So R of IT plus 1 by C into IT dt is equal to V. Now you can transform this signal. We know the R will remain same as R, and C can be converted. If you are confused with this, you can directly write the equation for this. We know the Laplace of IT is equal to IS. The Laplace of integral of a function is equal to IS by S plus Q0 by S, and outside is 1 by C. So if you can transform the sources, so transformation will lead to V. The Laplace of V is V by S. I written V by S. The Laplace of R is nothing but R itself. The Laplace of the C part, it gives as 1 by CS, and the initial value V0S by S. So whichever way, so writing the Laplace of this equation, you get R into IS plus 1 by C bracket IS by S plus either you can write V0 by S or Q0 by S, because Q0 by C will ultimately be equal as a V is equal to V by S. So therefore, you can write this as taking as IS as common, R plus 1 by CS is equal to V by S. Again, taking S on the top, R by S is common. So S plus 1 by RC, IS is equal to V by S. Transform this the other side. So you'll get IS is equal to rearranging this. So this whole part will go to the other side. You'll get V by R. S will get cancelled, and 1 over S plus RC. Now taking the inverse Laplace of this, we get I of t. IS will become as IT. V by R is a constant, and we know the Laplace of 1 over inverse Laplace of 1 over S plus 1 by RC. That is 1 over S plus A is equal to e power of minus AT. So therefore, the answer is IT is equal to V by R e power of minus T by RC. You are asked to find out the voltage across the. So this is IT. We know voltage across a resistor will be VR equal to RIT, R into IT. Multiply this by R, so you'll get VRN. So R will get cancelled. So therefore, this will be equal to simple as V into e power of minus T by RC. So this R will get cancelled. And we know what is the voltage across the capacitor. This is nothing but 1 by C integral of IT dt. So therefore, you can put the value of IT as this. So integrate it. Integrating this, you will get VCT is equal to V e power of V, and this part will get cancelled, e power of minus T by RC. So this way, we have seen the solution to 3 questions from the midterm examination of the last year for the circuits and systems. We'll see the solution of 2 more questions that requires little more time. So we'll deal with question number 4 in a separate video. Thank you for watching this video.